Good evening, everybody. Welcome to the British Computing Society Oxfordshire branch. In a moment, I'm going to introduce you to Robert, who's going to be talking to us about robotics in extreme environments. I will try and avoid making jokes about extreme environments in the US after yesterday's and this morning's results, but well, I suppose I did. So before I introduce Rob, I'd just like to remind everybody that we've got a very exciting Christmas lecture. Conrad Wolfram of Wolfram will be presenting on a wide range of topics, but the title is Computation and Society, Past, Present and Future, Key Perspectives as we enter the AI age. Those of you who know Wolfram will know about Mathematica and Wolfram Alpha as an AI tool, so it's got a long and strong history. And those of you who work in IT will realize that AI has always been here. It's just been rebranded recently to something more exciting. So Conrad Wolfram will be speaking here in this lecture theatre on the 4th of December between 7:30 and 9. I'd now like to introduce you to today's speaker. Robert Skilton is a head of robotics and research technology at the UK Atomic Energy Authority. This is an organisation that is developing fusion energy as a way of producing electricity in a much safer and greener fashion, and will be contributing to the energy demands in the future. Part of that is the robotic side of things, and Rob, I'm sure, is going to give you a very interesting presentation on all things robotics, both physical and digital. Over to you, Rob.
Thank you, Andrew. Good evening, everyone. So, as Andrew mentioned, my name is Rob Skilton. I'm head of robotics research and technology at UK Atomic Energy Authority. And this talk is on robotics in extreme environments. So I'm going to try and introduce what I mean by extreme environments, why we might want to do things in these extreme environments, a little bit about why robotics are relevant there, and then talk about some aspects of fusion. So a lot of this will be presenting some of the work that is going on at the UK Atomic Energy Authority today to help deliver fusion energy. And then look at some of the future developments, some of the outstanding challenges, and some of the work that's being done to help try to address some of those. So just to introduce myself a little bit further. So I like to think of my job as solving interesting robotics challenges in a way that helps take people out of harm's way and helps to clean up the environment. So that's something that I'm really happy and proud to work on. My background is in computer science, artificial intelligence, and cybernetics. And I've worked in this industry, robotics for extreme environments, in particular robotics for nuclear and fusion environments for roughly 15 years now. Local companies, Oxford Technologies, and then joining the UK Atomic Energy Authority 12 years ago, working on various collaborations related to fusion energy, related to robotics for nuclear decommissioning in the UK and Japan. And today I'm leading various research activities on the next generation of robotics for solving the future of fusion energy, which we'll obviously come back to later in the talk. So, when I say extreme environments, what do you think of? What makes an environment extreme? So we can think about different aspects of extremity. It could be high temperatures. It could be low temperatures. You might have explosive items. So we can think about defense contexts for extremities. There might be radiation or radiological hazards, magnetic fields, hazardous chemicals or corrosive chemicals, asphyxiation risks, trip hazards, gravitational hazards, risk of things falling on you, or biological hazards. So fundamentally, you could define this however you like, but when I talk about extreme environments, I'm really talking about environments which are not favorable or pleasant for humans to be in. So that could be things which are harmful to human health or just unpleasant because they're dull, dirty, or otherwise dangerous. So why would we want to go in these horrible, hazardous, harmful places? You know, the quote that came to mind when I first thought about that question is because it's there. The famous Mallory quote related to Everest, but it's human nature to explore the most extreme frontiers of our world. And, you know, some of the greatest achievements that are being had today are in the extreme environments, in the subsea regions, and space exploration. Another quote from Elon Musk, it will be a misquote, I can't remember exactly what he said, but we are at risk of extinction if we don't become a multiplanetary species. So perhaps these are good reasons to do things in these extreme environments. But there are also more mundane reasons to go into these extreme environments. And a lot of that stems from the fact that we simply need to get things done in places that aren't necessarily very pleasant or have hazards associated with them. So some examples of these, is this, I use this one, Andrew? What's that?
Use the mouse.
Use the mouse, okay. Yep. So we could think about infectious diseases. That's obviously something which is in the forefront of our minds from recent events. We can think about inspection and maintenance tasks for infrastructure where there are confined spaces and other hazards. Disaster relief. Earthquakes are something which I'm going to come back to in the talk. And it's very important to be able to do tasks to search and rescue people from inside these hazardous environments as quickly as possible. We might be talking about infrastructure inspection in sewers or mines, which are simply unpleasant to be in, and also extreme environments in terms of other infrastructure maintenance. So these are examples of areas where the environment is not somewhere that you would want a person to go, but because of the thing you want to do, this is it's important to do that. So we come to this concept of if we don't send a person into the environment, how do we get those things done? How can we keep the person in a nice, pleasant, safe environment and still do these things which we want to? And remote handling is a term which is used in particular in the nuclear industry for doing things remotely, doing things without being directly in the environment yourself. So I suspect most of you have some experience of remote handling. And the first thing I'm going to touch on is a little bit of historical aspects related to remote handling. So remote handling means doing things at a distance. And you can see some examples here of really simple tools which allow people to do things at a distance. We have blacksmith's tongs, which are used to prevent people from being harmed whilst doing tasks in this hot, dangerous environment. Cooking food, we have remote handling tools which are being used because perhaps the food is hot, but also we want to avoid contamination and things like this. Long-range pole tools for swimming pool maintenance. And then litter picking because we don't want to touch the litter and we don't want to have to bend over. So from this perspective, remote handling is something that most of you do on a day-to-day basis in some form and has certainly been around as a science for thousands of years. But in the 1940s and 50s, the nuclear industry took this to a new level where we started handling some really dangerous things and wanted to keep people well away from those. So the types of devices you see on the screen are mechanically coupled manipulators. So they have two arms, which are separated by a thick wall with a viewing window, usually leaded glass or some sort of protective glass, so that the operator can handle these hazardous materials through these clever cable-coupled mechanisms, whilst looking through a shielded window to be able to do the task on the other side. So that allowed us to do some of these amazing nuclear things, amazing and terrible nuclear things that were developed during the nuclear revolution. A little bit later on, 1950s and 60s, I don't know where exactly this started, but certainly some activity took place in the US and in Italy. And these mechanically coupled manipulator arms suddenly became coupled by electricity. So this is one example of an early variant of the mascot manipulator, which we'll come back to. And this was coupled rather than by steel cables transmitting the forces from one arm to the next, by electricity and closed-loop control. That allowed the devices to be separated by cables, by electricity, which meant they could be separated by many hundreds of meters rather than only a few meters at a time. There's a really good video online, if anyone cares to look for it, of this being demonstrated at a conference where a man in the audience is being shaved by someone operating this remotely. And it's also used to light people's cigarettes. It shows the age of the video. But the extreme environment that I'm going to start talking about really is this one. This is a nuclear fusion reactor. It's the JET reactor, the Joint European Torus. And it's possibly less of a hazardous environment than a lot of the things that we've seen before, but still the sort of environment where you wouldn't want to send people unnecessarily. This is a fusion reactor, and the reason we want to go into this extreme environment is because we want to maintain and upgrade and operate this device so that we can do amazing science with the mission of delivering fusion energy as a sustainable power source of the future. So that's our mission, and that's what we want to do in this environment. JET, for those of you who don't know, is fairly close to here. We're in Oxford, and JET is located at Culham, which is just a few kilometers to the south in Oxfordshire, and it's been operating since the 1980s. It's been operating for 40 years and has recently gone into decommissioning. It's reached the end of its scientific life, although the robotics and remote handling technologies that I'll talk about are still in use. So we looked at some of examples of simpler and historic remote handling, remote maintenance technologies. JET, the state-of-the-art manipulator, the state-of-the-art technology that's being used there today is this device called the Mascot 6 manipulator. It's an evolution of the electrically coupled device in the historic photo, and it's been developed by UK AEA for over a decade to give world-leading performance in terms of handling things remotely. So the way this works is an operator sits in a remote control environment, in a safe, clean, normal office environment with good lighting and perhaps a cup of coffee, and monitors what's going on remotely using camera views displayed on a screen, whilst operating the arms, which move the remote arm inside the fusion reactor in a manner that allows him to control the motions and interact with the environment. The system also provides force feedback, so the operator can feel everything that happens in that remote environment as if they were really there. And that's really important for doing dexterous tasks. That's really difficult to do. So one of the challenges of designing and building a system like that is that you have so many different stages from one end to the other. So from the operator to the remote environment, you end up going through the mechanical arms, electrical motors, electrical systems, communication systems, software, And then on the other side, back into communications, back into electric systems, motors, arms, and the environment. So there's this long chain of things which contribute to the performance of a manipulator like this. And what that means is that it's very difficult to design and build and test systems like this. So it has to be done in a very iterative manner. So this is what you end up with. This is the mascot manipulator. This is the operator using it. And you can see two mascot systems here playing Jenga against each other. So this gives you an idea of the sensitivity and the force dexterity available in this sort of system. And that is the dexterity that allows us to do really intricate tasks like making electrical connectors or feeding electrical cables into narrow spaces without causing any damage to the environment. So this is showcases the capability of these types of systems, but it's also not just a demonstration. These systems are really difficult to use as well. It takes months for an operator to train to the competency level that's required for doing maintenance inside somewhere like a fusion reactor. And so these methods, like playing Jenga, are actually used as training aids and as tools for retaining skill between different campaigns where these devices are being operated. A manipulator like this in JET is delivered to its work location on long-reach boom robots. So this is an example of a long-reach boom robot. It has lots of joints along the way. This one's roughly 10 meters long. And the reason for doing this is that fusion reactors typically have tight constraints on how you can get in and out of them. A lot of the fusion reactors today have ports on the side of them, which means you need to enter through the side and then reach in over a very long distance through a narrow port, which means you have a long, slender arm reaching into deep space, which mechanically is very awkward. It's really not what you want to do because you have a heavy load being carried over a long distance on a cantilever, and it makes it very challenging. We also have issues where, because the device is made as slender as possible so that it can fit through those narrow ports, you end up with elements being less strong in terms of elasticity than you would like them to be. So you end up with elastic behaviors, and you end up with long things that vibrate. And that causes problems. And these are some of the challenges that need to be dealt with for accurate positioning of systems inside a delicate environment like a fusion reactor. There are also tools which need to be developed specifically for this type of device. So at JET, UK AEA have developed, I think, over 600 different tools specifically designed for this type of device. So when we think about using a generic robot for doing a wide range of diverse tasks inside an environment, that means we often need to adapt that robot using tools as you would a human pair of hands to doing the task at hand. So a lot of these are modified conventional hand tools, modified conventional power tools, or some are completely bespoke tools for the fusion environment. But because it's difficult to operate things with tools remotely with camera views and force feedback only, there's been a series of evolutions of technologies to help make the use of these tools as easy as possible. So things like color coding and gripper interfaces that guide the grip into the right location, pins to stop accidental dropping of tools, and things like visual indicators, spirit levels, or LED indicators to show that things are docked or aligned properly. So lots of thinking has gone into these types of tooling and capabilities. And of course, it's not just about physical tools. A large proportion of the enabling capability is in the digital tools. So these robots don't drive themselves, and they don't make plans themselves. So there's a whole suite of digital tools employed for something like the JET remote maintenance system, which includes graphical user interfaces, software interfaces for the operators to control the robots and control the functions, as well as digital planning tools, procedure tools, databases, and virtual reality digital twin technology. And this kind of technology is used for training operators before they get to the real equipment, much like you would with a flight simulator. For feasibility studies, equipment reviews, and developing tasks offline. It's used for control and peer review of tasks. So there's a lot of process and control that goes into these types of environments. And also to support live operations with additional views and additional information. So virtual reality technology and digital twin simulations has been something that's been used at JET since the 1990s, really one of the early adopters of that sort of technology. And what you can see here is some videos of some of the remote virtual reality technology that's used to support operations at JET and in many other locations. So this technology is a software platform built on top of the Unreal game engine technology, if any of you are familiar with that, but really designed specifically and engineered very carefully to provide features that allow an operations team to plan and execute remote operations. So that's exactly what it's designed and intended for. And of course, all of that is not a series of just discrete elements. These are all integrated together. And they really come together along with the team of expert operators in a remote control room. So this is where all of the physical hardware connectivity, the streams of videos, the software, and the operations come together, and a team of 3 to 5 people operate something like the JET remote maintenance system from an environment like this. So overall, this is the JET facility, and this is what remote maintenance inside JET looks like. We have a digital twin and physical robots that go into the remote environment. There's lighting that's brought in, as well as cameras. And those camera views are used to remotely install, remove components, and do all manner of tasks: cleaning, diagnostic, calibration, anything that's required for the next series of scientific experiments. So that's JET. And JET is really historically one of the most interesting facilities where remote robotics and robotic maintenance in a facility has been developed. There are very few examples of exactly that level of robotics being used for those sorts of things elsewhere. This is where I work. This is a facility called RACE, which was set up in 2015 to take the lessons learned from JET and take all of that experience and see where it could be used elsewhere. So look at where it could be used to support future fusion devices, but also where it might be relevant to places beyond fusion, other challenging and extreme environments. So I'm going to look a little bit for the next few slides in some other extreme environments where we've taken this technology and explored where there is relevance. So for those of you in the room, does anyone know where this is? Lots of nods. So in March 11th, 2011, there was a large earthquake off the coast of Japan, which created a tsunami. It was a terrible disaster. And one aspect of that was that the conditions led to a nuclear accident at the Fukushima Daiichi nuclear power plant in Japan, which this is a photo of. And that got a few of us thinking that a lot of the situation, there are lots of big differences between fusion robotics and what's been done at JET and a scenario like this. But there are some overlaps and there is some commonality. And if you're responsible for operating a nuclear power plant in Japan, and overnight, your responsibility becomes very different. And your expectation is to decommission a nuclear disaster and clean it up. That's a very difficult thing to transition into. So we began talking with the team in Japan, and it became clear that some of the most interesting things that we might be able to do to explore where there might be commonality would be to look at the use of digital and physical mock-ups, digital twins, the virtual reality technologies, the digital systems, and how some of those lessons learned from JET might be transferred to places like Fukushima Daiichi, and how digital twins could help de-risk robotic nuclear decommissioning operations in Japan and beyond, in the UK as well. So we undertook this 4-year program. We're now just stepping into the next phase of that. But it was focused on this task of digital twins for de-risking nuclear decommissioning operations. And that included things like exploring digital twin technologies. We put together a series of research studies associated with lots of different aspects of that. How you can compensate for some of those flexible vibrations and deformations in systems, how you might bring the sense of touch into simulation so that you can train operators more easily for these types of operations, and how you might bring things like artificial intelligence and image processing in to help deal with some of the tasks that have to be done. And one slightly different aspect to the collaboration was about the robotic manipulators themselves. What you can see here is a device, actually 2 different devices there. So these are nuclear telemanipulator robots. You can buy these off the shelf if you have deep enough pockets. And they are readily available for doing tasks in your nuclear reactor. We were interested in characterizing the performance of these. So you get to a very difficult question when you are faced with a task that needs to be done, a difficult handling task. And you have to answer the question, how much performance do I need? How dexterous does my manipulator need to be? Can I get away with the 100,000 pound robot, or do I need to buy the 5 million pound robot for the task that I have? So quantifying and establishing the difficulty of tasks, but also the performance of these types of manipulator systems, along with their human operators, was one of the things that we were really interested in doing. It's also interesting from the perspective of operator training. So I mentioned it takes many months to develop competence sufficient for doing something like maintaining a fusion reactor. Can you improve that? And how can you measure how much that training improves performance? And when you introduce new technologies like augmented reality or haptics, the sense of touch, into your training scenario, how much faster does that make the training? So these are the questions that we wanted to try to answer with these types of systems. And we didn't answer them all, but we did manage to chip away at those a little bit. And if you do have a 5 million pound manipulator system that you want your operator team to use, how many do you need to buy for them all to be able to train simultaneously, or to be able to train in some sort of reasonable timescale? The answer tends to be that you only have one, because that's all you can afford. So actually training becomes very difficult on these types of systems because you don't have access to it as much as you would like, and you don't have parallel access for multiple people. So one of the things we explored in this work was, how do these digital technologies translate to training in a haptic sense? Can you physically interact with the environment in a way that allows you to do training without having access to these very expensive and often used systems. And I mentioned dealing with vibrations. This is an image of one of the systems which is actually sat in Japan at the moment. So this is a long telescopic boom robot. It's concertinaed up here, so it unfolds as it enters the environment. And a lot of the work that we did was focused on how do you model the dynamics of such a system? How can you capture how it's going to vibrate and how it's going to flexibly deform and sag as it's going into a reactor? And then can you compensate for that? Can you use intelligent control strategies to reduce those vibrations and bring it under control sufficiently that you can accurately move in and do the task that needs to be done? For example, retrieving some fuel debris from inside the reactor. Another extreme environment, or a collection of extreme environments. Does anyone know where this one is? Windscale. It's the Sellafield site. Windscale is part of it. So this is northwest England, and it's one of the largest nuclear sites in Europe. It's very densely packed with lots of facilities that have historically been used for nuclear energy research, nuclear tasks, fuel reprocessing, and a whole manner of other things. One of the challenges that's faced is these things. These are glove boxes. So glove boxes are something which is commonly used in many industries. So I guess you could call this an alternative to remote handling. This is just protective handling. Typically, operators will look through a window and use protective gloves, rubber gloves, or other materials of glove to handle things in a isolated environment. So the operator is protected from the hazard inside. Also, the thing inside is protected from the operator. So these are used in food manufacture and medicine manufacture for those reasons. Exactly. But in any case, they're environments where you want to keep a separation between the operator and the thing being handled. These nuclear glove boxes tend to have unpleasant hazardous materials inside them. And one of the challenges faced is where you close facilities and end up with hundreds of glove boxes like this left behind, how do you clean them out and prepare them for whatever your waste route is? Typically, you'll have to clean them out, separate the materials, pack them into containers, ideally separate out the hazardous material from non-hazardous material. So that's a big challenge, and there are real safety risks associated with doing the types of tasks involved here. If you think about a rubber glove, it's not going to give you very much protection from, for example, sharp objects or crushing hazards. And there have been some accidents that have taken place in these sorts of environments. So another area that we explored where the technology from JET could be reapplied and help benefit other sectors is looking at how remotely operated robotic systems could be used for handling materials inside of these legacy glove boxes. So can we take the operator's hand out of the glove port and put a robot in and separate the operator into a comfortable, safe, remote environment? So this is some video footage from a project called RAIN, Robotics and AI in Nuclear, which was a collaboration between the UK AEA and 10 universities across the UK to explore how remotely operated technology, as well as autonomous robotics, could be used to do some of these tasks to take people out of harm's way as much as possible. I suspect no one knows where this is, maybe some of the UK AEA people. So we've talked a bit about fusion and about nuclear decommissioning, but we can also think about other big science projects, so high energy physics experiments. This is the European spallation source. It's a neutron source, which is being built at the moment in Sweden. And it is the largest of its kind and will provide some amazing science for researchers from all around the world. But in the process of producing these neutrons through this process called spallation, it produces some very highly radioactive items which need to be cut up and packaged. So we have led the way in providing this facility. It's a really interesting facility where you looked at the hot cell facilities with the windows and the glove boxes. This is essentially a 15 meter by 15 meter by 15 meter one of those. It's an environment which is kept separate from people, and all of the tasks that need to be done in this environment will need to be done completely remotely for several decades of operation of this facility. So it could be 40 years. And what that means is saws, cutting equipment, milling equipment, handling systems, all of the associated cleaning functions, viewing functions, everything that needs to be done in there needs to be done reliably for decades, completely remotely, whilst any maintenance, upgrade, repair is also done remotely. So that's the sort of environment where you start to really see that actually this is not a very easy problem to solve. And you could, again, think about a spacecraft or something like that as perhaps the equivalent of this type of environment from lack of access. So this is being built. Some of the manipulator systems you saw earlier, the Valishmiller Telbot, are being prepared for use in this environment. And it's really quite fascinating, and I think presents some of the really cutting edge of where robotics are used in extreme environments for scientific experimentation. But back to fusion. So JET has demonstrated some really amazing capability, and in many ways it's been the incubator for remote technology, for robotics in extreme environments, in particular in nuclear environments. And you might think, well, it's solved then. But unfortunately not. This is an artist concept of STEP, the UK's fusion experiment, which is being built in West Burton in UK over the next couple of years, over the next decade or so. This is ITER. And what you start to see here is that as you start to move more towards fusion power plants from JET, which was an experimental device, through ITER, which is being built in the south of France as an experimental device, towards future fusion power plants, you start to see an increase in scale, an increase in complexity, and an increase in the level of the hazards that are involved. So higher temperatures, higher levels of radiation, dozens of parallel operations that need to take place, and levels of complexity, which means inevitably much more maintenance needs to take place. So when we look at that, we see that there are lots of outstanding challenges, and in fact, fusion is really difficult to achieve for many reasons. Fusion as an energy source. One of those reasons is that you don't just need fusion energy, you need fusion energy that reliably generates electricity and makes a profit for the people who build the fusion power plants. And the only way you can achieve that is by having fusion reactors that can be readily, quickly, and reliably maintained, which means that in these extreme environments, we need to be able to do a whole manner of maintenance, inspection tasks very quickly and reliably. So because we know that this is such a big challenge, we've identified the top challenges for robotics in fusion energy. and distilled them into a document which you can find on our website, and you'll be able to find this quite easily. But it identifies what we think are the top 10 major challenges for remote maintenance and robotics in fusion energy. The reason we've done this, as UK Atomic Energy Authority, is to lead the way. So we're interested in solving these problems. We're interested in communicating what the problems are so that the world's best experts in various technologies can help us to solve these. And we're interested in collaborating to solve these challenges. I'm not going to go through all of these in detail. I will just mention the first two. So architecture optimization. The easiest fusion power plant to maintain is one that requires no maintenance. That's a really important thing. And a lot of the things we can do to make maintenance more reliable and more fast are by reducing the complexity of that maintenance and making it easier to do. So we're very interested in how we optimize the designs of plants to make them more readily maintainable. The second is really interesting one. So this is about service joining. And when I say services, largely I'm talking about pipes. So we can describe ourselves as the tokamak plumbers, as you will. Service joining is really important because we have done some calculations and worked out that roughly 70% of the time taken to maintain a fusion power plant is breaking and making pipe connections. So that means cutting pipes and then re-welding pipes and inspecting them to make sure that those welds are reliable. And that needs to be done remotely from inside or outside the pipe in these extreme environments. So I'm not going to go through the other 8. Feel free to do that as homework. But I am going to look at some of the bits of research that is ongoing today aimed at addressing some of these. Arguably, this is not robotics. What is robotics? But it is in an extreme environment, and it is very important, and I'd be negligent to not talk about pipe welding in a talk on fusion maintenance. Speed and reliability are really key, and lasers potentially can do these tasks much, much faster than conventional methods. So some of the things that we're looking at today involve using lasers for cutting, re-welding pipes, but also for things like inspection. So we're looking at some really interesting techniques using lasers to do ultrasonic testing inside pipes. And that's a really interesting thing with lots of potential, both for doing the types of defect detection that we need to do, but also for the extreme environments. We're also very interested in the idea of in situ maintenance. So what that means is, rather than removing components and taking them to a workshop environment where we can comfortably maintain them, which may take months, if we detect minor defects in a component inside a fusion reactor, can we send a robot to it and repair it where it is using additive manufacturing techniques, subtractive manufacturing techniques, or a number of other options? So this might be pipes, or it might be metallic tiles, it might be ceramic coatings on things. And the question is really, can we repair it where it is quickly and efficiently and reliably without having to spend a long time removing lots of things and putting them back? Here you can see some experimental trials. So this is looking at some of the robotics aspects of that exact problem. This is looking at using a combination of serial robot manipulators with parallel delta robots to explore additive manufacturing, in this case, using plastic 3D printing technologies to explore how robots can work together for some of these problems, but also to start to look at what some of the problems are of robot delivery of this sort of technology into some of the problematic areas that we face. Okay. Another area is simply dealing with the extreme conditions in those environments. So we've mentioned radiation, we've mentioned high temperatures. Both of those things have significant impact on robotic systems. And if you took any conventional robotic system that you can buy off the shelf today and put it into one of these extreme environments, you would generally find it fails very quickly and may not be able to get any use out of it whatsoever. Typical robotics have various aspects. And if we look at the challenges of radiation, you'll see problems associated with three main areas. One is semiconductor electronics, the second is optics, and the third is polymer materials, so plastics used in robots. So if we're to leverage the amazing advances of robotics that are taking place today with things like Spot and self-driving cars and humanoid robots, all of these things which are rapidly evolving, we need to solve these more fundamental problems so that those robots don't just fail within minutes. So this is a very interesting and important area of investigation. Some of the things we're looking at are things like different ways of laying out components on the silicon, but also different substrates. Can you use, instead of silicon, things like silicon carbide or gallium arsenide, or even diamond, some of the things we're looking at the moment. And there's some really interesting work ongoing to look at how you develop technologies that are just inherently resilient to these harsh conditions. Remote visibility of the environment. So one of the things that I mentioned was operators using flat screens with camera views to see what's going on. Why don't we use 3D displays? Why don't we use virtual reality headsets for, or stereoscopic headsets for remote viewing? There are lots of reasons that they're not practical. And some of the things relate to bandwidth and latency. So operators tend to need very fast information. Some of the issues relate to the ability of those operators to communicate with the teams around them. This was a piece of work that was actually looking at, can you do remote operations with a robot across different continents, across the internet? And the question that was raised here was, can you transmit information sufficiently for an operator to do a nuclear decommissioning task, in this case in South Korea, from the UK over the internet, using 3D reconstruction? So looking at clever ways of compressing and transmitting the most relevant information for the task at hand so that an operator can use a robot remotely. Another collaboration with Korea, I mentioned extreme environments, and this is really the most extreme environment. So when you're operating a fusion reactor, one question that arises, if something looks abnormal, is your fusion reactor safe to use? Can you run another pulse? And it's really difficult to answer. So what you would ideally have is something that you could send in very quickly, within, say, an hour, do an inspection and see if everything's as it should be. What that means is you have to have something ready to go in that most extreme environment, the highest levels of radiation, the highest temperatures, vacuum conditions, magnetic fields. And we're exploring long-reach manipulated technologies that do exactly that. These are tendon-driven robot arms, so they're manipulated remotely using steel cables with no onboard sensitive components, which can go in within hours and explore, rapidly inspect conditions in those most extreme conditions. I mentioned architecture optimization. So I imagine some people in this talk are interested in optimization techniques, generative design, those sorts of things. So what you're seeing here is some of the work that's ongoing in terms of automatically generating and optimizing robotic systems for these extreme environments. So if you have a definition of what that environment is, Can you rapidly optimize a robot system so that it's idealized to go into that environment? Can you work out exactly how many links you need, how long they should be, and how the dynamics of that are going to perform? And when you have those long, slender, flexible payloads, how do you control the vibrations of those? So I've touched on this a bit. I think I'll skip on slightly. Okay. So just a couple more areas of innovation and ongoing research. One of the challenges we face in long-lived facilities is this question of how do you build a system such that in 10 years' time, when technology around you has completely changed, you can pick up those new technologies and rapidly integrate them into what you're doing to take the benefits? Or how do you go into a nuclear reactor that has been through a disaster and you don't know exactly what the conditions are or what needs to be done? How do you design a system to cope with that? And one answer to that is that you design methods to make your system architecture highly agile and highly modifiable. So this is a piece of work that's been ongoing for several years at UKAA, looking at digital systems that promote interoperability between robotic systems of systems in hazardous environments. So you can think of USB connection as an interoperable standard. This is something that allows you to plug multiple devices into your PC and rapidly use them without having to do too much. So how do you apply that technology to sensors, actuators, robot devices, heating systems, lighting systems, whatever it is in these environments, so that you can have Lego bricks of capability that can be reconfigured for the task that you have at hand? And one of the ways we've addressed that is through some interesting standardized data representations and communications protocols that allow you to rapidly reconfigure robotic systems whilst minimizing the propagation of the impact of that. I like to end with a Spot video because everyone loves Spot. This is a really interesting piece of work, and it's quite interesting in many ways. This is a collaboration between us and the Oxford University here, Oxford Robotics Institute, who are great at this sort of thing. It's really about trust. What we did was deployed a robot into a fusion environment. This is the jet reactor hall, and had it do routine inspection patrols twice a day for 35 days consecutively with no human intervention through that entire period. So this was really about testing, can we do it? Can we get a robot in situ to do the routine inspection patrols every day, twice a day, without needing a human to go and intervene? Can we get the processes and safety systems and so on in place and demonstrate that this is possible and build trust in autonomous robots for doing these sorts of tasks in high consequence environments? And it went really well. And I think it shows that the robotics technology, autonomous robotics technology, is really not only making great progress, but also gaining a lot of reliability, which is fascinating. So this robot was patrolling. It was doing photographic surveys, geometric surveys with point cloud data, measuring temperature, humidity, radiation levels, a whole manner of things on a twice daily schedule, allowing us to do automatic change detection and research into a whole load of things with the data that came out of that. So this is the sort of data that comes when you put a LiDAR system on a robot and drive it around very useful set of data that gives you geometric measurements related to the environment. And finally, I just want to point out that everything I've presented is the work of some pretty amazing teams that are working at Culham at the moment. So all of this is about people, and I always tell people when asked what is the most interesting or even the most challenging thing about doing robotics in extreme environments, and definitely working with people is the most interesting and rewarding thing that we get to do. These are some amazing award-winning teams, and yeah, thanks to them for this amazing work that's been displayed today. And that's all. In summary, we've looked at some extreme environments. We've talked about jet and nuclear fusion, and then looked at where the lessons learned from those environments can be reapplied to other hazardous scenarios, and some of the future of what is being developed to help enable the future of fusion. So hopefully we're heading in the right direction, and that this will allow us to deliver fusion energy in the near future, as well as help to clean up some of those nuclear disasters and other unfavorable conditions around the world. So thanks very much for having me, and very happy to take any questions.
Rob, if you take some questions on the floor,
sure.
I'm just going to wander around with the microphone so that remote people can hear us as well. We've got a couple of questions online. If you are online and you want to pose a question, please don't put it in the chat, put it in the Q&A, and then we'll pass those to Rob as well.
Yeah.
First of all, thank you very much. Very interesting talk. I had one question. It doesn't seem as if you've got any end-to-end full automations. You didn't mention that. And it would seem that, in robotics, the expectation is high on automation. But it seems that, for example, manual manipulators are still, there's a human operator, and it's very much a human-based activity.
Yeah.
I think you referred to a little bit at the end, looking at automated planning for, standardized operations. But I was wondering if today you're doing anything which is fully automated to standardize routines and things like that.
Only really simple things. So most of what we see in fusion and wider nuclear industry in terms of robotics is remotely operated. As we move into the facilities that are being delivered today, like ITER, there is definitely some work taking place to do automated trials, automated operations in those environments. It's still fairly limited, and I think part of that is due to the fact that the environments are often not quite as controlled as you would like them to be for doing the sorts of things that you would do on a maintenance line, on a production line, for example. So we are looking at automation. Automation is one of our key research areas for this sort of environment, as is full autonomy with the mobile inspection robots and things like that. But the majority of what's being done today is still, teleoperated. And another aspect to that is the safety and trust and regulatory issues. So it's sort of the standard practice to trust human operators to do work as they are, and deviating from that is quite difficult. So establishing trust for changing the way things are done to more automated and more autonomous ways is quite challenging sometimes.
Thank you.
Any other questions in the room? Yes.
Thank you very much. It was a very nice talk, and very happy to see the type of work you're doing and carry on the good work. I just had a question in regards to the sensors that you used. I think you covered a little bit and looking at like the LiDAR and things that were done by the robot. Is there kind of experiments looking at quantum sensors, for example, to bring in some of the finer tune sense information that could create better feedback for the robotics?
Not very much, but it is something which is being explored, in particular quantum imaging sensors. So there's a hub here in the UK called the Quantic Hub, Quantum Imaging Technology, which we have engaged with for these types of challenges to some extent. But it's definitely not the sort of core of what's going on. A lot of what we're looking at today is conventional sensing methods and how they can be modified to cope with the environment. So generally thinking about simple sensing technologies. Thank you.
Let's take some online questions.
We can do that. Here. Rob, you might be able to see them up there, but anyway, we got a couple from Remy online.
Yep.
First one is around how much of a regulatory hurdle do you face when building these systems for the nuclear industry? Is it easy to translate the legal requirements into technical requirements?
Yeah, and it's a complex issue. One answer is it varies quite a lot. So when we're talking about fusion energy or talking about nuclear decommissioning operations, we're often talking about facilities in multiple countries where the regulators are quite different. There are different regulators and they have very different rules and restrictions. In the UK, we have the difference between nuclear facilities like Sellafield, which is regulated by the Office of Nuclear Regulation, and fusion, which is regulated through the Environment Agency. There are all sorts of challenges related to that. Some of them do feed into requirements of these types of systems and solutions. And in some cases, the regulatory environments that we're working with aren't compatible with the technologies that we're trying to use. So there is definitely some consideration of regulatory requirements in the design of these systems, but there also has to be some dialogue and some work with the regulators to help shape what those regulations are so that we can do what we need to in these really unusual situations that, and in particular with technologies that are evolving rapidly, really in some cases leaving old regulations irrelevant or needing improvements. So it definitely has to be a dialogue there.
Okay, thanks very much. Another question from somebody else this time. How far have you got with communicating with robots using radio signals rather than through direct links?
It's yeah, it's a really good question, and this is something that I've thought about a lot over several years. So you can think about radiation tolerance of wireless communications, Wi-Fi systems, and things like that. But quite often with robotics in extreme environments, we end up going back to older analog technologies. And one question that I think naturally arises, perhaps that's just me, is can you use analog radio to control some of these systems remotely? And as far as I know, no one's done that. But I think it's something we should look at. And if anyone's aware of technologies like that we should look at, please let me know. Yeah, really good question.
Any more questions in the audience here? Any more online?
We have a few. So another one from Remy. In your slide around challenges in robotics, can you expand a bit more on what you mean by the handling of challenging components? Is it challenging because of the design stroke fragility of the component itself, or is it challenging because of the logistics stroke supply chain?
So the slide is really referring to the component itself, nothing to do with the supply chain. What we're talking about is things which are just difficult to handle. So you might imagine flexible components, articulated components which are just very big and heavy. There are all sorts of ways that a thing can be difficult to carry. And if you think about carrying awkward objects yourself, some objects are really easy to carry and have handles and nicely centralized centers of mass. Others are just really awkward to handle. And we end up tending to have to handle a lot of those awkward ones. It might also be things like fragility, so things that we don't want to damage or break. It might be things like just awkward shapes where we can't find a good place to grasp it. So they're the sorts of things that I'm referring to when we talk about handling challenging components. And if you look at a fusion reactor design, you see lots of things with very obscure geometry, very unusual geometry, and lots of very large components. So you can imagine they're the sorts of things that we're generally trying to move around very precisely.
Okay, thanks very much. Next one, how far have you got with in situ maintenance regarding metal additive manufacturing? What sort of materials are the focus at the moment?
Yeah, so good question. And it's really difficult. So in terms of additive manufacturing to repair components, we're looking at mainly steels and tungsten. So for steels, additive manufacturing processes are pretty well established and work pretty well. But translating that to an in situ operation where it's deployed over a long robot and doing additive manufacturing in an area where you have limited sensing and ability to control the environment, that's where the difficulties come in. With tungsten, which is often used in fusion devices, the simple additive manufacturing process itself is quite difficult. So we're at earlier phases when it comes to that. But yeah, lots of interesting opportunities for innovation there, I think.
Another live question.
I need to try and remember to stay where the camera is.
Thank you again. I was just reading about the fine motor movements. Have you also worked on using ultrasonic sound for moving of components in a very fine, controlled way?
No, but another very good question. And I don't know if you're aware, there's a company called Haptics, which is doing perhaps the other side of that, providing force feedback using ultrasonic actuators. I think ultrasonics for moving components and things like piezoelectric actuators for moving components, in some situations, that might make a lot of sense. No, it's not something that we've done so far. Yeah. Yeah. Interesting question, though.
We've got quite a lot more questions now. We've got quite a lot more questions. We can either answer them one by one, or we can type answers at the end of the talk. Which would you prefer, and people in the room as well?
What do you prefer in the room?
Interesting questions.
Okay.
Can we
all
fill
interesting questions? I have to say that.
I'll leave that to Andy.
Okay, so well. Feel free to leave if you need to, and Rob, please feel free to draw a close when you've had enough. The next one I don't understand, but I'll try it anyway. What would be the most friendly conductor for IC dev? And I only don't understand it because I don't know the acronym. Does it mean something to you, Rob?
Integrated circuit development?
Possibly, yes.
I don't know. It's not my area of expertise. I really have very little knowledge in that area.
Sorry, Salo. We'll have to find somebody else.
Sorry.
Another question from Remy. General question, but what is in your opinion the biggest barrier to innovation in robotics in general, but also curious about specifically robotics in extreme environment?
I need to be very careful how I answer that. So I would say let's rephrase it. One of the biggest opportunities for innovation in robotics and robotics for extreme environments. I put up a slide briefly looking at how artificial intelligence techniques could be used for design of robotic systems and could be used for optimizing and co-designing robotic systems. I think one of the biggest opportunities these days for doing more, for rapidly innovating in robotics is exploring that field of generative design and automated AI-assisted optimization of robot systems, including the mechanics, including the control systems, all aspects of that, I think is probably the biggest opportunity there. And I think one of the barriers there is when you think about robots in extreme environments and innovation, what might you think about as barriers? Things like funding, things like safety, regulation constraints, bureaucratic organizations. I think all of those play some aspect, play some part. But yeah, I think there's definitely opportunity for assistance in rapidly exploring concepts in safe environments, which I think is something we need to do a lot more of.
Okay, next one. Most of the robotics you describe are for maintenance in a shutdown environment. What is being done for in-service maintenance of routine tasks when a reactor is operating?
Yeah, so it's an interesting question, and I say extreme environments. So when you have a fusion reactor, you have a very extreme environment in the middle of it, and you have a full spectrum of other environments from that right through to completely benign office environments. Although not all office environments are that benign. So shutdown situations, typically you'll do those operations in the most extreme environments where there's not a practical ability to go and do things during operations. The work with the mobile quadruped inspection and things like that, I think we'll start to see a lot more of that sort of thing used for routine operations, routine inspection and maintenance during operations as well. The difficulty with in situ maintenance during operations is, well, you have the extreme environment and you have the fact that you don't want to interrupt those operations. So you need to be very careful and very reliable in those most challenging of environments. So it's a very difficult thing to do. It is a research topic for us, but I don't see that it will be a routine thing for anything other than very simple operations in the near future. Should we do one more? I think we're starting to see people drop out.
Yeah. Okay. So last one. Could you please elaborate a bit on how you achieve the hardening of electronic components to withstand high radiation environments?
So, okay, just generally for hardening of systems, when we talk about electronic systems or systems as a whole, we talk about different approaches. So we have segregation, shielding, separation, shielding, replacement, and by design. So we can put lead shielding around the component, which is typically impractical. And I was trying to find examples of this a few weeks ago, and I found no examples of lead shielding being used in robotic maintenance systems because it's too heavy and thick. We have an approach called separation, which means separating the sensitive components by a long distance. So that typically means leaving some part of the sensor in situ and separating the sensitive, say, electronic parts by long wires over hundreds of meters into a safe area so that we can do those operations. That's typically used very regularly. We have substitution, which means we take a sensitive component like a optical encoder and replace it with something which is less sensitive, an analog equivalent like a resolver or a potentiometer. And then we have finally radiation hardening by design, which is generally the most expensive and difficult thing to do, which is about replacing that system with one designed from scratch for that environment. And that means the sorts of things that I was talking about, changing the way that the components are laid out on the silicon substrate, changing the substrate material itself, or substituting other usually quite exotic materials that are less prone to those radiation conditions, radiation damage. So they're the sorts of approaches we tend to take.
Fantastic. So I think we'll draw the questions to a close there. Thank you very much, Robert, for an absolutely fascinating talk. And I think everybody would like to give you a round of applause again.
Thank you for having me.